Hello again, and welcome to Astronomy Toronto. My name is Randy Attwood, and I'm your host, and also President of the Toronto Centre of the Royal Astronomical Society of Canada. Well, on this edition of Astronomy Toronto, we're going to be talking about a very, very interesting topic, a topic which most people think of when they talk about astronomy, and that is black holes. And my guest has had a very important past in the research of black holes. He's Dr. Tom Bolton, who is at the David Dunlap Observatory in Richmond Hill and at the University of Toronto. Thanks very much, Tom, for coming on Astronomy Toronto today.
Thanks, Randy. It's a pleasure to be here, although I'm not sure that I entirely appreciate you talking about my very important past. Would like to think I have a future as well.
Well, there's certainly a lot we want to talk about today, Tom, with regard to black holes. And I guess the first question I have is for everyone out there, what are we talking about when we talk about black holes?
Well, I think what we're talking about initially is something that is predicted by theory. In the simplest terms, a black hole is an object that has such a large gravitational field that light cannot escape from it. And since light is the fastest moving thing in the universe, at least of material or electromagnetic radiation, that means that nothing can escape. So lots of things can go in, nothing can come back out. We cannot know of the character of the interior of a black hole.
How long have we've been thinking about black holes, their existence in space?
Oh, 70 years or thereabouts. The black holes are a prediction of the theory of general relativity, although even in Newtonian physics, going back several hundred years, the general concept of something like a black hole existed because the idea of escape velocity in things from bodies. The light has a certain speed, and if you could imagine a body that was massive enough, which would have to be something very, very large, then the escape velocity could be greater than that of the velocity of light, and it couldn't escape. But there's a difference between the two conceptions, because in the Newtonian conception, there is no limiting velocity. Velocities could be larger than the velocity of light. The whole basis of relativity is the constancy of the velocity of light, and that's an upper limit to the velocity. And so the character of a body like a black hole is different as predicted by the two theories.
And we know of just a few black holes today of existence, some candidates?
We have some candidates. I think we can't say that we know for certain of any black holes. We have several bodies in the universe that we very strongly suspect they are black holes. If they're not black holes, they're something that are so unusual that they are very different from anything we understand in context of ordinary physics today.
Well, we're talking about black holes with Dr. Tom Bolton of the David Dunlap Observatory, and a black hole being a very old and dead star, I guess, or a star that has reached the end of its lifetime. Why don't we talk a bit about now about stars in general, and could you tell me about the general lifetimes of stars, how stars are born and how they die, so we can understand black holes a little bit better?
Well, when a star originally forms out of the interstellar medium, it's a large cloud of gas which collapses into a ball where there is a balance of forces between the pressure which is produced by energy generated within the star by the fusing of hydrogen atoms to produce helium initially, and the gravity which is trying to collapse the star. And those two forces remain in balance in a situation which we call hydrostatic equilibrium. And the sun is an example of a star, a big ball of gas, where these two forces are in balance. And as long as those two forces remain in balance, the star will just sit there looking the same. But as the star burns up hydrogen, changing it into helium, it begins to exhaust its fuel, and in order to maintain its balance between these forces, it undergoes changes in the interior. And those changes cause the interior of the star to collapse, to become more compact, and at the same time the outer layers, quite paradoxically, expand, so the star becomes larger and redder. And there are a sequence of changes that go on then As the star alternately expands and contracts as new fuel sources turn on, as the interior of the star gets hotter, those are exhausted, the star contracts, it becomes hotter, new fuel sources turn on, and meanwhile the outer layers are expanding and contracting on very long time scales. Now we're talking about time scales of billions of years in the case of a star like the sun. Now exactly what happens depends on how big the star is. If you have a star like the sun, after 10 billion years or so, the fuel is exhausted, it goes through some of these changes, starts to burn helium as the next fuel. Helium, it turns out, is the last fuel available to a star with a rather low mass like the sun. The sun is not a big star as stars go. And once it's exhausted helium, it has no other fuel source. And so there's no way to balance this contraction of gravity. And it contracts, and it just continues to contract until the forces between the electrons in the nucleus of the star provide enough to stop this collapse of gravity. And that's a body called a white dwarf. They have the size about like the size of the Earth, but the mass of the sun. So they're incredibly dense objects. Now, if the star is somewhat more massive, say 6, 8, 10 times the mass of the sun, then it can burn carbon after it burns helium. But the conditions in the center of the star when the carbon is burned are such that the carbon doesn't burn quiescently. When the carbon is burned, it all goes up at once, and you get a humongous explosion.
Now, it doesn't reach the point where it can burn the carbon because of the temperature inside, right? It's directly related to the mass.
That's right. In order to be burn, the carbon has to get to high enough temperature so the particles are moving fast enough to overcome the repulsion from the electrical fields in the nucleus. You're trying to put two positively charged particles together and make them stick, and the electrical forces are very strong. So unless the temperatures are very high, you can't get that to happen. And it's only in the most massive stars, or the more massive stars, that carbon can be burned. As I say, that takes place under conditions that once it starts, all of the energy is released instantaneously, and the star blows itself apart, really. It blows the outer layers off, the inner part collapses until the electrons are forced into the protons, and you get a neutral particle, a neutron, and you wind up with something called a neutron star. And neutron stars are about 10 kilometers in diameter. They have about a mass of about a solar mass. So all the rest of the mass of the star has been blown away in this huge supernova explosion. And you're left with this incredibly dense object. Now, remember, 10 kilometers in diameter for this star compared to an object like a white dwarf, which has roughly the same mass, but is the size of the Earth. So this is really dense stuff.
This is the thing you hear about. If you had a spoonful of a neutron star material, it would weigh the weight of several mountains, or
yeah, 30 million tons, I think is the number that I remember.
Number,
yeah, it's a huge number. It really doesn't make sense to even think about it in those terms.
Yeah. Now, some of these supernovas that you mentioned have been seen. If a star blows up in our galaxy,
oh, yes,
we have seen supernovas in the past.
Indeed we have. It's been a long time since we've seen one in our galaxy. I think it's been going on 400 years now, but that's probably because we live down in the plane of the galaxy. There's lots of dust, so we can't see the entire galaxy. We see them every year in other galaxies.
Yeah, and these supernovas are so bright that, well, some of the recent ones, they're stars that you can actually see in the daytime. Isn't that right?
Oh, yes. Oh, yes. The ones that we know about in our own galaxy, in fact, were observed before the invention of the telescope. So they had to be naked eye, or people didn't know about them. Yeah. And they would become as bright as the planet Venus, or even much brighter than that, and easily be seen with the naked eye in the daytime.
So how many solar masses would the star have to be? And that is, how many masses equal to, or of the sun, to become a neutron star?
Oh, around 10 solar masses, probably.
Okay.
And then up to about maybe 20, 25 solar masses, 30, we're not real sure of those numbers, you'll get the same process. Above that, the masses become high enough that you can burn, that the carbon burning takes place slowly, quiescently, and Other elements can be burned as well. You produce silicon can burn. You can burn right up to iron. Now, iron is the last element that you can fuse the nuclei together. Above that, the nuclear charges are just too high, too many electrons or protons there. They're 26 in iron, so you're trying to overcome too much electrical repulsion. And what happens is the star gets hotter and hotter, the iron nuclei start to become unstable and want to break down into the elements they were before. But in the process of building up to iron, there has been energy lost at each step of this, which helped to support the star and produce the light that we see from the surface. And now, when the iron starts to break down, it has to take energy from the star to get back to these lighter nuclei. And so it's sucking energy out of the star, and the star just collapses on itself or implodes. A process that we don't really understand very well theoretically yet, and we've never observed it because it takes place in a very short time scale. But we think because the star is so massive that the star just keeps collapsing on itself, and there is no force in nature that is strong enough to stop the collapse. It collapses indefinitely to the point that the gravitational field becomes so strong because the star is so dense and compact that it effectively just wraps space around itself, and nothing can escape from this star. It has what's called an event horizon in general relativity around it, and once something crosses an event horizon going into this object, the escape velocity or the curvature of space is such that it can't escape, even if we're talking about light rays, and so we have a black hole. Things can go in, but no signal, nothing can propagate back out from the interior of this object.
Now, what you've told me is all theory, and had to be theory up to a certain point.
Right.
Until astronomers were ready to start looking for them.
Well, I think astronomers started looking for them as soon as the theory was promulgated, this goes back, as I say, 70 or 80 years. But the problem is, what do you look for? I mean, you're looking for something that can't send light to you, has no way of propagating a signal to you. It's going to be a very small object. It's smaller even maybe, well, it's as small as a neutron star. The only effect that it has on the universe around it is through the gravitational field. And so it's a very difficult thing to find a black hole.
We have a chart, and if we could bring the chart up on the screen, you'll get an idea of how actually dense a black hole would have to be. Could you explain this chart to us, Tom?
Well, a black hole can be an object in principle of any size. We've been talking about stellar black holes, stars that become black holes. But in principle, you could take any kind of object and compress it enough so it would become a black hole. And on the chart, we see the sun here, as an example of a star, would have a diameter of about 3 kilometers, and the density measured at the edge of this event horizon, which is the 3 kilometers, the radius of the object, is very small, or very high density. But you can see for a 200-pound man, the size of the object is a tiny fraction of a centimeter, something very dense again. But you notice as you go to larger and larger objects, the size of the black hole, the physical size, becomes larger and larger, and the densities become smaller, to the point where if you imagined the universe as a black hole, say the density of the universe was large enough that it became a black hole, or it might even be, in effect, a black hole, then the size encompasses the entire universe. We're talking about something very large, so it doesn't follow the usual rules that we're used to in terms of relationships between size, density, gravitational field.
Well, whenever we're talking about black holes, a lot of things don't follow the rules that we're really used to.
Certainly true.
Well, let's talk about a certain black hole, the first black hole candidate, which was Cygnus X-1, and what experience you had with it trying to determine that it was a black hole.
All right, well, I think we have a picture here at the beginning. One of the difficult things is to identify which objects might be black holes. And the real breakthrough in the field came in the late 1960s when X-ray telescopes were launched above the Earth's atmosphere. They have to be above the Earth's atmosphere because X-rays don't penetrate to the ground.
Sure.
And they found that there were some 70 to 100 strong X-ray sources. And they fairly quickly found that some of these appeared to be in binary stars because they observed eclipses as the X-ray source went behind a companion star.
Okay, and a binary star, again, is just...
Two stars orbiting about each other just like a planet orbits about the sun.
Right, okay.
We thought in the beginning that these X-ray sources would be neutron stars, that you would have gas being torn off the companion star and falling onto this very dense neutron star, being accelerated at very high velocities, and it bangs into the neutron star and releases a lot of energy. And that energy comes out in the form of X-rays. There's a lot of heat there, so it's very hot. People had kicked around the idea that some of these might be black holes, but it wasn't taken very seriously. I mean, the idea of black holes had been around for 60 years by then, and we hadn't found one, so they kind of lost credibility as realistic objects. Also, there was a problem of how do you get the X-rays out of a black hole. Remember that I said that no signal can come from a black hole. It turns out there is a way you can get X-rays from around a black hole, not in a black hole. But as the material falls in, it will spiral in and form an accretion disk of hot gas around it, and it has to give up energy to fall into the black hole, and it does that by radiating it away in the form of X-rays.
So what we're seeing is not the black hole itself.
Not the black hole, but the material falling into the black hole, spiraling into the black hole. Well, so you want to go out and look at these X-ray sources. And one of the strongest of these was a source called Cygnus X-1, the first X-ray source discovered in the constellation Cygnus, which was thought at that time to have eclipses. And the picture we saw on the screen a while ago showed a picture, an optical picture of the region of where that X-ray source was, and the boxes that were drawn on there were the rough positions taken from the X-ray data. And you can see there that there are a lot of stars in there, which makes it very tough for optical astronomers. Which star do you go and look at to see if it's a binary? But quite fortuitously, a radio source turned on in the position of Cygnus X-1 at the same time as the X-ray properties changed, which meant that the events just had to be agree with each other, same object. Both effects.
Suddenly a radio source.
Suddenly a radio source turned on when the X-rays actually declined in intensity.
So you'd see this as the star would be going around?
No,
this was a single event?
This was just a single event.
Okay.
And what was nice about this is you can get very accurate positions with radio telescopes. And the radio telescopes pointed and said, this is the star you want to look at. And so I went out with the telescope at the David Dunlap Observatory, and some other people went out with other telescopes and began to observe this star to see if we could establish that it was a binary star. And what I was looking for, at least with the telescope we just saw on the screen, was to get an orbit to find the mass of a neutron star. I really thought that was something we didn't know and we wanted to know at the time, and it seemed like a good way to do it because it was an eclipsing binary. Well, what we saw when we look with the telescope, I think, is shown in the next slide that we have. There's a spectrum of the star shown with the spectra of some of the other stars. Yes, we see here the spectra of actually several stars are shown here. These are actually negatives, with the dark band being the light from the star, and it's interrupted by some light lines, which are absorption from gas in the outer parts of the star. So they remove some of the light from the spectrum.
So in a sense, a spectra is just an elemental signature, I guess? You're sort of looking at the light?
Signature of what's there in the atmosphere of the star.
So you're looking at the different elements of the star.
That's right, but that signature tells us something about the mass of the star, the temperature of the star, and by watching as the lines shift back and forth in the spectrum because of the motion of the star, we can tell whether it's a binary, or if they don't shift, it's not a binary. And that's effectively what we were doing. We were measuring the shifts of the spectral lines caused by the Doppler effect. The lines are shifted to the red if the star is going away from us. They're shifted to the blue if it's coming towards us. I think there's a schematic diagram in the we have that demonstrates that effect. No, we've skipped over that.
Okay, what are we looking at here?
This is actually the results of observing Cygnus X-1. We have the velocity curve, which you can see goes up and down periodically. Time goes along the horizontal axis here, and the velocity is in the vertical axis. And as time goes on, you see the velocity first increases and then decreases. And it does this periodically with a period of 5.6 days, which is the signature of a binary star. Now, the surprise here was that rather than the velocity varying by give or take 20 kilometers a second or 10 kilometers a second, as we would have expected because we knew that the companion star here was very massive from its spectrum, 20, 30 solar masses. Neutron stars were expected to have masses, solar mass. So you wouldn't have much effect on the velocity of this big companion star with this little thing trying to swing it around. But the velocity here varied by plus or minus 70 kilometers a second, maybe 3, 4, 5 times as much as you expect for a neutron star, which indicated that there was an unseen star in the system that was extremely massive, and it apparently was also an X-ray source. And that's exactly what you expect to see from a black hole. And it was the first good evidence that we had indeed found a black hole.
Okay, we have another slide coming up here, Tom, which is, again, it's like a big detective story when you're looking for a black hole, putting all of the, the evidence together and coming up with a black hole. If we can look at the next slide, we should see an artist's depiction. Is that what we think it might look like?
That's an artist's depiction of what it should look like. The velocity curve by itself is very strong suggestive or presumptive evidence that it's a black hole, but you really need other pieces of evidence. One of those pieces of evidence is the light curve. If there was a massive star near the star that's shown, the blue star that's shown here in conception, it distorts the star into an egg shape. And as that star rotates, as the two stars orbit about each other, the light from the star varies. You see the star fainter when you're looking at the small end of the egg, and you see it bigger when you're looking at the large cross-section of the egg. And we saw that too. We could work out the masses. It turns out that the companion here that we don't see has a mass of about 10 to 15 solar masses. Actually, we think 15 is closer to it with modern data. And it's got all the properties that you would expect from a black hole. But the important thing to remember here is that we have not proven that it's a black hole. None of these observations prove it's a black hole. They indicate it has properties like you would expect from a black hole, but really what we have done is ruled out it being a neutron star or a white dwarf, because the theory tells us, and the observations tell us as well, that neutron stars and white dwarfs don't have masses as large as 10 or 15 solar masses. And then they're not, we don't think they can have masses that large. So this is a process by induction, really. And as long as we have thought of all the possibilities, you could say that we've proved it's a black hole. But there's always the possibility that our theoretical ideas are not complete and that there are possibilities that we haven't thought of. So we really haven't proven that there's a black hole there. And the same story is true for all of the other systems.
For all science, of course. So what's the next step? Something like better telescopes or newer ideas?
Unless we get some new theoretical ideas about tests that can be made from the ground, the only way that we're going to prove that there is a black hole there is by actually going close enough to the system to be able to study, to resolve it and look at the details of how light behaves around the black hole, how matter behaves around it.
And that's still a far way off.
That's a long way off. This object is the closest one known. It is about 8,000 light years away and is well beyond the realm of possibility that we could travel there in foreseeable future.
And you're still working on this problem?
We have completed the last of our observations and submitted those for publication. We have just carried out a large study of other stars looking for other potential candidates using particular selection criteria related to what you'd expect from supernovae explosions. And I'm sorry to say we found nothing.
Oh, that's too bad.
It's very disappointing.
That's fascinating, very fascinating, Tom. Thanks very much for being on Astronomy Toronto.
My pleasure.
And I'd like to thank you for watching. A reminder about Halley's Comet. Astronomy Toronto will be live on Thursday, December 5th at 8 p.m. with a live phone-in show. Any questions you have about Halley's Comet, be sure to watch and phone them in. For Astronomy Toronto and Dr. Tom Bolton, my guest, I'm Randy Attwood. Thanks again for watching.